Linear Optimizer for GroupFair Learning and Optimization by Daniel Alabi, Nicole Immorlica, and Adam Kalai, and Daniel will give the talk.
Hello. OK, it works. Hey, I'm Daniel. I'm going to be talking about unleashing linear optimizers for GroupFair Learning and Optimization. Joint work with Nicole Immorlica and Adam Kalai, both at Microsoft Research. OK, so I just wanted to start with a slide concerning the World Cup. What do we know so far? We know the Argentina football team pretty much reduces to Messi. And now the question we're trying to ask is, can any continuous Lipschitz continuous GroupFair function reduce the calls to an approximate linear optimizer? And it turns out the question is yes. And now I'm going to define what group fairness is. The intuition for group fairness is that no group of individuals should be treated unfairly. So if we have a statistic about a partition of the feature set, or a partition of all the members of a group, then we don't want the statistic to differ too much across groups. And I'm going to talk about specific GroupFair functions in later slides. All right, so formally, if we have overlapping groups, possibly overlapping groups, x1 all the way to xk, we define a fair function, and we're trying to minimize the unfairness between outcomes of groups. And there's also a notion of individual fairness, which I'm not going to talk about here, but it pretty much says that similar individuals should be treated similarly according to some metric. There's a similarity metric people define for that. All right, so our work is concerned with GroupFair reductions, by which we mean that we're trying to optimize a function f, and we reduce it to calls to a linear optimizer. And here's some previous work about it. For a 5ML ICML paper to be presented, they specify convex constraints that can be folded into the objective. And demographic parity and equalized odds, which are both GroupFair functions, GroupFair notions, can be specified like this. But demographic parity, by the way, means that the result of a classification for an individual should be independent of the group to which the individual belongs to. Equalized odds means that the result of a classification for an individual, given the true label, should be independent of the membership of the group. The group membership of the individual. And then there's other works that can handle convex functions and a ratio of linear functions like gmean and f1, which is f1 is the harmonic mean of the precision and recall. And there's also work that can handle non-decreasing functions, but then this needs access to a projected attribute during classification, and our work kind of bypasses that. All right, so our work can handle any Lipschitz continuous objective of group losses. Group losses includes things like the false positive rate and the false negative rate. So here's an example. Suppose we have this following non-convex objective that combines the misclassification rate, which is the first term, and then tries to reduce the disparity between loan approvals for males and loan approvals for females. And that's encapsulated in the second term. Now, this is how it actually looks, and that's the feasible set over there. And I think that green line, I don't know why it's cut up, but that green line should be the global minima, and then the red line represents the local. And so the goal is to try to reach that global minima, and this contours just show that it's easy to get to the local minima, which is quite close to the global minima. And so we want to apply some kind of gradient strategy to avoid that. All right, so formally, here's our function. And we're trying to minimize this function f, which could be non-convex, to within epsilon over the classifier set. And so LKC represents the loss incurred by a group K. You can think of it that way. And now, what are we going to use? We're going to use an approximate linear optimizer, which is defined as follows. And then we're going to use a loss assessor. And the loss assessor pretty much means an approximation to the loss within a tau tolerance. And then we're going to have oracle access to the function f, to the Lipschitz continuous function f. All right, so here's the theorem. We, for any constant k, for any epsilon between 0 and 1, can minimize to within epsilon using tolerance equal to epsilon squared over 25 root k. And calls to L tau, M tau, and f, which is polynomial in 1 over epsilon. So remember, L tau is the loss assessor, which approximates the true loss. M tau is the linear optimizer within tau. And f is just the function we're trying to minimize. And so an example is fair facility location. So suppose we have an oracle that can minimize that pretty much solves the facility location problem for, let's say, the group in orange and then the group in gray. And the goal is to then define a new function like this. And so what we're saying is that we can use the minimizer for each group to then optimize such a function that combines that's an objective of both the groups, like this. And so like a very succinct description of the algorithm is that, so we pretty much grid the space. We define grid space in equals to that value, epsilon over 5 root k. And then using number of calls, which is 1 over epsilon squared, times log 1 over epsilon squared, we then call the linear optimizer, m tau. And then for the t iterations, we receive like a different classifier. And then once we have a certain range, we return a classifier that's uniformly chosen amongst all the classifiers we've chosen so far. And the intuition is that after we grid the space, for the best classifier C star, there must exist some grid point R star, which is close to C star. And so we just try to find that R star which is close to C star, and then use the linear optimizer to reach that goal. And the algorithm is pretty much Frank-Wolf, but with gradient. So Frank-Wolf is a conditional gradient descent algorithm, as opposed to gradient descent, where you, like, every time you move into what's a negative gradient, you always have to project back to the set. For Frank-Wolf, you don't actually have to do that, because projections can be expensive. All right, so here's the algorithm. I don't have time to go over it. And so in our paper, we also show that fair optimization implies fair learning, in that if you have, yeah, so this is pretty much learn results. All right, so the idea for the learning result is that, remember L tau was the loss assessor, M tau was the linear optimizer. We just use a polynomial number of examples to simulate both L tau and M tau. All right, so here's the summary of the applications in the paper. I've talked about fair classification, but we also extend it to fair regression in that we can just minimize squared errors. We can minimize using loss assessors, which are squared error functions. And then we also talk about how to extend it to the convex group optimization case. For the more general setting, actually, like our runtime is exponential in the number of groups, the constant number of groups. But then if we're trying to minimize the convex function instead, it's going to be a polynomial number of groups. And we also show this in the paper, also by reduction to linear optimizers. And here's the recap. Thanks.
Time for a quick question while the next speaker is getting ready. Please.
I think so, yeah. It is unavoidable because we have like a similar example. Yeah, it's unavoidable. We can talk about it in post session. And like also, I believe, I don't know where Ilyas is, but he also like has, his thesis, I believe, was about multi-objective optimization, and he shows that for multi-objective optimization, like you need to have an exponential number of objectives you have. And our case is reducible to that. And so it's unavoidable.
All right, let's thank Daniel again.